Good day, Dr. Amal. We are from Group 2, Section 3. So today we are going to present our report for high voltage laboratory for experiment 2 design project using finite element mathematics. So our group consists of 4 members, which is myself, Christopher, Ishad, Muhammad Uwais, and so Muhammad Amirin Haikat. So for task 1, analysis of electrode field between electrodes, myself, Christopher, and also Ishad will present for the task 1 part. So moving on to the introduction of our project. So from this experiment in electric field analysis laboratory, we are using finite element mathematics (FEMM) as our simulation software. So it is an essential tool for modern electrical engineering, able to build models, and so we are able to understand electric field phenomena. From this, we are able to gain hands-on exercises with sphere gaps for voltage measurement, as well as to develop skills for real-world high voltage transmission issues. So next, the background of our study. So from this electric field analysis, it is essential for evaluating high voltage systems. So it is critical for improving system performance and also safety. It highlights the significance of electric fields and also the current densities. It is crucial for developing and also evaluating high voltage equipment. So FEM finite element method effectively handles electromagnetic problems. It is able to investigate electric fields using FEMM software. So from this, we're able to study the system behavior at different sphere gaps length. So the objectives for task 1 have 3. So the first objective is the use of FMM to simulate and analyze electric fields between electrodes and also incorporating materials properties and also boundary conditions. So the second objective is to identify the regions of high electric field intensity and also compute average field utilization factors. And the third objective is to able to calculate the maximum electric field strength at various field gap distance. So moving on onto the scopes for the task 1, we have 5 scopes. So the first scope is to develop a comprehensive electric field model in FAMM software using grounded sphere gaps. And the second scope is to investigate the system behavior at sphere gap distance from 1 centimeter to 17.5 centimeter. And the third scope is to able to evaluate the disparity between simulated and calculated maximum electric field values. And the fourth scope is to able to determine the fuel utilization factor for all gap lengths to assess the efficiency. And the last scope is to able to analyze the correlation between fuel utilization factor and also the electric field.
Assalamualaikum warahmatullahi wabarakatuh. My name is Irsyad Syami bin Rusaini. Metric number DE210109. Okay, for methodology, flowchart. Start with create electrode model in FEMM software with gap distance of 1 cm, and then define properties for high voltage electrode with height value of 31.4 kV, ground electrode with ground properties, and outer boundary with outer boundary properties. And then run mesh generator and click hand crank and big magnifying glass to run the result, and then set the density plot with field intensity plot, and then set the line plot between gap distance of the electrodes, and then display graph for voltage versus graph distance and maximum electric field Emax versus graph gap distance, and then record and analyze the result. Repeat the simulation with gap distance of 1.5 cm, 2 cm, 2.5 cm, 3 cm, 3.5 cm, 4 cm, 5 cm, 7.5 cm, 10 cm, 12.5 cm, 15 cm, and 17.5 cm for voltage value of 44.7 kV, 58 kV, 71.5 kV, 85 kV, 97 kV, 110 kV, 136 kV, 196 kV, 268 kV, 294 kV, 331 kV, and last one is the 362 kV respectively. Next, we move for the result. For gap distance 1 cm and voltage 31.4 kV, the Emax gain is 3.211 megavolt per meter. And then for distance, gap distance 1.5 cm and voltage 44.7 kV, Emax is 3.059 megavolt per meter. Then for gap distance 2 cm, voltage 55 kV, Emax gain is 2.999 megavolt per meter. Then gap distance 2.5 cm, voltage 71.5 kV, Emax is 2.973 megavolt per meter. For gap distance 3 cm, voltage 85 kV, Emax gain is 2.961 megavolt per meter. For gap distance 3.5 cm, voltage 97 kV, Emax gain is 2.920 megavolt per meter. Next, gap distance 4 cm, voltage 110 kV, Emax is 2.917 megavolt per meter. Then gap distance 5 cm, voltage 136 kV, Emax also 2.917 megavolt per meter. Then gap distance 7.5 cm, voltage 196 kV, Emax gain is 2.895 megavolt per meter. Okay, for gap distance 10 cm, voltage 268 kV, the Emax is 3.061 megavolt per meter. Then gap distance 12.5 cm, voltage 294 kV, Emax gain is 2.776 megavolt per meter. Then the gap distance 15 cm, voltage 331 kV, Emax is 2.684 megavolt per meter. And the last one for gap distance 7.5 cm, voltage is 362 kV, the Emax gain is 2.591 megavolt per meter. Okay, for discussion, this is the graph gain from the result, which is the maximum electric field Emax versus gap distance. We can see from this graph depicts a decrease in electric field with increasing gap distance between electrode. This phenomena is attributed to the intensifying force between charged particles as electrode get closer, and the rate of electric field increase tapers off at smaller gaps due to diminishing voltage influence. The graph serves as a tool to predict and prevent such stress by visualizing the impact of conductor spacing on electric field intensity.
So now I'll continue the presentation for the question part. So the first question is to calculate the error of the maximum electric field between simulation and also calculation value for every gap distance. So this is the manual calculation for the gap distance of 17.5 centimeter. So the calculated maximum electric field for 36.2 kilovolt and gap distance of 17.5 centimeter is 2.5 megavolt per meter, and the error calculated is 3.09%. So this is the summarization for the calculation of the error of the maximum electric field between the simulation and the calculation for all the gap distance between 1 centimeter to 17.5 centimeter. So from this table, we can see the summarization. So for gap distance of 1 centimeter, the error is the highest, which is 11.41%. And whereas the for gap distance of 17.5 centimeter, it shows the lowest error, which is 3.09%. So for question 2 is using the maximum electric field values from simulation, calculate the field utilization factor for all the gap lengths using this formula. So this is the utilization factor formula for, so this is the example calculation for 17.5 centimeter gap distance. The calculated utilization factor is 0.7984. Okay, so this is a summarization for the calculated utilization factor for all the gap lengths from 1 centimeter to 17.5 centimeter. So from this summarization, we can see the uniformity level for all gap distance is uniform. So for question 3, so this is the answer. In response to question 3, the field utilization factor measures electrode configuration uniformity. So higher N values signify a more uniform electric field. So this factor determined by operational parameters heavily influences electrode effectiveness. So greater N leads to a more efficient and so evenly distributed electrode arrangements. For example, 1 centimeter gap distance corresponds to utilization of 0.9778. So high N optimizes electrode configuration for efficiency, resulting in a more homogeneous electric field between electrodes. So moving on to the last question. So why is it important to evaluate a maximum electric field in high voltage application? So the answer is understanding the maximum electric field in high voltage application is paramount. It ensures the construction of resilient insulation systems capable of withstanding peak strains while minimizing failures and also electrical sparks. So this evaluation is crucial for ensuring the dependability of components, enhancing system efficiency, and also adhering to safety regulations, ultimately safeguarding both equipments and also workers.
Okay, for conclusion, FEMM software can be used to simulate electric field around the power lines to help identify the high risk areas and improve the overall design for safety and efficiency. The space between conductors and the design of the conductors themselves both affect the intensity of the electric field. By optimizing these factors, power line design can be improved.
So these are all the references for task 1 report. So that's all from us. So we will pass to the next member of the group to present the task 2.
Hello and Assalamualaikum. We will present for the task 2 that is analysis of force of a gap CI core. For the background of study for the task 2 that is optimizing the performance of different electromagnetic device require a thorough understanding of force in a gap CI core. When there is a gap in the core, the magnetic circuit is drastically changed, affecting the device overall properties and behavior. Comprehending the force at play is imperative to improve the design and efficiency of this core. Several techniques are used to precisely calculate the force in gap CI core under both DC and AC conditions such as FEA analysis. Okay, for the objective part, there is two objective. That is to analyze an open boundary condition of an unbounded problem, and the second one is to understand the concept of leakage flux, mutual flux, framing effect, and the force exerted in an electromagnetic system. Okay, for the scope of the task 2, that is first one, the use of FEMM version 4.2 software. Second one, the number of term will be set as 500 permanently and the distance will be set as 0.1 permanently.
Next is result and discussion for task 2. For the force accepted value for 0.1 cm gap distance, we have get negative 145.087 n for x component and negative 0.0159492 n for y component. Meanwhile, for 100 cm gap distance, we get negative 0.000122591 n for x component and 1.13083 e exponent negative 0.007 n for y component. As you can see at the C core or at the pink region, that is the highest flux density region. Next is field intensity. So the gap between the CI core have the highest field intensity region. For current density, so as you can see, the pink region shows the highest current density for AWGYU. Next for discussion, so the larger gaps will decrease the density. High permeability will increase the field intensity and current density. Magnetic field lines concentrated in high current density region. And lastly, accurate simulation will optimize the magnetic device performance. For conclusion, using simulation to examine the CI core model has yielded important information on the capabilities and potential areas for development of the system. Next, strong current flow in the coils of the C core is essential for generating the strong magnetic field required for efficient lifting. And lastly, by employing modeling technique like FEMM, engineers can predict the behavior of magnetic lifter, which help them better design and optimize the system for specific application. That's all from us. Thank you.